presentation will be given by Dr. Nattapong Chayawatto from KMUTT on the topic Energy System Optimization, the case for sector coupling. Dr. Nattapong, the next 30 minutes is yours.
Yes, can you see my slide?
Yes, perfect.
Yes. Thank you very much, Ajahn Sunirat, for your introduction. And good morning and good afternoon, everyone. I'm going to present the topic sector couple engine system with PISA. This one is very important for the PISA. So this is the subtopic. I will make a presentation. I will start with a formalization of optimization modeling approach. In this slide is more or less the same with Tristan, just give you the presentation. And then I move to the what is sector couple engine system. I will talk about what is the meaning of the sector couple in terms of supply side and the demand side. And the last thing, I will show you the case study. I use case study from the PISA website, and actually because of the time limitation, and that's why I select only 2 simple case study from the PISA website. So you can see the concept for the optimization is more or less the same with Tristan just presentation. PISA can optimize the dispatch of generation and storage unit, and also can optimize capacity of the generation, storage, and transmission infrastructure by using cost optimum. In terms of the cost optimum, we use the annualized capital cost and the marginal cost under the constraint, for example, to achieve the energy demand in each sector, and also the constraint of the transmission line, and also the constraint from the renewable energy, especially for the variability of time series, and also from the geographical potential. If you remember from the Ep10 presentation, we need such kind of the data from the Ep10 to include for the constraint for the optimization. And also it's a popular issue for the carbon neutrality. For the carbon limitation, it's one of the constraints can be included in the PISA. And also we can include the flexibility from the gas turbine, battery, hydrogen, or HVDC link into the one of the constraints for the PISA model based on the cost optimization. So I move to the meaning of the sector couple or the energy system. For the energy system, the PISA can add the demand and supply sector to the grids and storage. The example of the sector couple, for example, is a transport sector. We can include the EV to the energy system with the PISA, and also we can include the space and water heating in residential sector or commercial sector to the PISA. And also we can add biomass or energy consumption in various sectors. For example, from the agriculture, and the information for the consumption from industrial sector, and also for the carbon management, carbon capture and utilization, we can include in the PISA. And one thing is keep in mind, PISA cannot include for the waste management and agriculture, forestry, and land use and land cover. So you can see in the right hand side, this is very diagram to show the overview of the sector and the links. On the left hand side is show the supply side or source side, and the middle show the grid system and storage, and the right side show the demand side. We can see the link between source, grid, and storage and demand side. For example, for the wind and solar PV energy, it can generate electricity and go to the grid system, and the electricity can transmit to the demand side, for example, for the electric device, and also can go to the heater or the heat pump, and then go to the industrial sector here. And apart from the wind and solar PV, we can add the hydroelectricity or biogas or fossil gas and biomass. And one of interesting we call the atmosphere is represent the CO2 emission in the atmosphere. We can input the data for the CO2 emission, and so we can do the component we call the direct air capture. I will show you in my case study as well. And also we can input for the carbon capture. And yeah, this is the overall of the sector and the link for the sector couple using on the PISA. So I move to for my first case study I will show you. As I told you, I got this example from the PISA website. This is a simple case study. This case study is a battery electric vehicle aim to optimize the size of PV panel. We can see on the right hand side, we have the node we call the bus or the place of the office, the place of works. And in this bus, there is a PV panel installation with a capital cost. For example, in this case, it's 1,000. And also in the office, they have the charger, and for the charging the EV. And in this case study, we have the assumption for the battery electric vehicle we call the BEV. And normally the driver use the BEV in the morning period for the 100 kilometer in the morning, and drive back to home in the evening for the 100 kilometer as well. This is like BEV uses for 2 times a day. And for the charging duration, can be get the electricity from the PV panel. We can see on the right hand side the PV panel installed at the place of work, or I call the office. And the last thing, the battery in the EV, the sizing is 100 kilowatt hour, and in the consumption of the battery is 0.18 kilowatt hour per kilometer. This is the data will be used for this case study. In this slide, it shows the input data. On the left hand side, it shows the petrol usage of the BEV. As I said, the battery will be used during for the driving from the home to the office in 2 times, in the morning and evening period. And after that, the battery will be charged during the daytime, starting from the 8 o'clock until 19 o'clock. So, and the right hand side is available of the charging. The middle is show like the PV profile, and the right hand side is show the availability of the charging. This is the input information we have to enter in the right. We have to write the script in the PISA. This is only the overall to give just the idea how can we do the modeling on the PISA. As we know, the PISA is based on the Python language. And on your left-hand side, we start with the import, the packages. One of the important packages we call the PISA. And also we have to import for the pandas or matplotlib. And then we have to input the information for the consumption pattern of the BEV. We can see in the time series only one day. In this case study, we assume it can be happen on the 2016 is 1st January. So after we input the pattern of the usage of the BEV, and then we have to input the PV profile in that day. And also we have to input the data for the charging period or charging availability. And on the right-hand side, we have to initiate for the network. We have to identify the bus, we call the office. We have to identify the battery. And so we have to input the create, we call the PV panel. We call the create with we call the component is a generator, is a name is a PV panel. And then we have to input the load. The load is mean like the pattern of the battery. So and then we have to create the link. It's like it's name of the charger, and that's it for the data for in this case study. And then we run optimization. We just type the command for the optimization. But the thing you have to write the script based on the Python. So this is the result for this case study. As I said, for this case study, we do the optimization of the PV panel sizing. And the result, you can get the optimum panel sizing is about 7 kilowatt. And so we can see the operation for the energy output and the state of charge during the day. And we can see the blue color represent its energy output. You can see the energy output from battery for to drive the motor for the electric vehicle. It can generate. It can use in this time for the driving from home to the office, and also it's a 2 times a day. And so we can see the state of charge. And in this period, it's a discharge for the battery to the motor. And after go to the office, there will be the period of the charging from the PV panel. And for my presentation today, I do not analyze in detail, but I just give you the overall how can we do the modeling based on the PISA. So I moved to my last case study. This one I call the biomass synthetic fuels and carbon management. This one a little bit more complicated compared with the previous case study. But in this case study, it's aimed to manage different biomass stock. That means in this study, they have 2 biomass power plant. We try to compare which one should be like the cost optimization with the different potential and cost, and the program will select based on the cost optimization. And also the component or the sector copying will include the fuel synthetic fuel production and direct air capture, DAC, and the carbon capture. The target in this case study try to achieve the net negative emission over the period. That means we try to achieve the CO2 reduction. For the assumption, the load, it can be for the electricity, it can be for the demand for the transport. And also we have the hydrogen production using the electrolysis process, and also there is a storage for the hydrogen. And also there is the diesel production from the hydrogen, and for the CO2 using the future stove and storage, we have the diesel storage after get the diesel production. And also in this case study, they have the CO2 emission to the atmosphere. And the last one, in this case study, we will call the DAC or direct air capture. For this component, consume the electricity to take the CO2 from the air to the underground or the CCS. This is the assumption. So this is like the diagram for the overall of this case study is a little bit complicated. We can start from the left-hand side. We have the node for the transport, the demand from the transport, and we have the diesel car, and also we have the diesel production. The result from the diesel car, it can emit the CO2 carbon dioxide in the air, and then the output from the diesel car will go to the CO2 atmosphere, and also there we have the stove to get the data for the CO2 atmosphere. And also in this case study, we have the open cycle gas turbine with the CCS. We have the open cycle gas turbine without the CCS. And so we have, as I said, we have the direct air capture in order to capture the CO2 emission in the atmosphere into the CO2 store or the carbon capture. And also we have the feature scope for the diesel production. To do this, we need the input from the hydrogen production and the CO2 to do the process of the feature scope. And on the right-hand side, we have the node for the hydrogen production. We have the hydrogen storage. To get the hydrogen, we have to use the electrolysis process. That means we have to use the electricity to for the process of electrolysis. And so on the bottom, on the right-hand side, we have the electricity bus. And also, as I said, we have the biomass power plant. We have biomass power plant with the CCS is one, and the biomass power plant with CCS 2. But for the two biomass power plant is different with the marginal cost and the number of the feedstock. And the software will do the calculation for the cost optimization. So this is the overall for the diagram in this case study. And so we have the gas bus for the gas storage to be like the input fuel for the OCGT power plant. So we go to the result. In this result, we can see the behavior of the storage. One of the highlight in this result, we can see the on the lower line is in the green color represent the CO2 from the atmosphere. We can see the CO2 from the atmosphere go down to 50 tons of CO2 because in this model we set up the CO2 limitation. You can see here. This is for the we set the case of the CO2 limitation is 50 tons of the CO2 equivalent. And when we run the simulation, we can see the graph is show we can fulfill for the CO2 reduction. This is from the atmosphere, and also To do this, we need some the CO2 storage because we cannot mitigate or we cannot reduce the CO2 from the atmosphere without using the carbon capture. We can see the amount of the CO2 or carbon capture increase. Yeah, this is the highlight for the simulation, and also we can see the trend of the value of the natural gas they use for in this snapshot. And so this is the biomass feedstock 1 and feedstock 2. We can see the software can choose for the biomass stock 1 and stock 2 based on the cost optimization. In the snapshot from the 0 to 6, we don't need to operate for the biomass stock 1, and for the stock 2 they do the operation based on the cost optimization. And so we can see the term of the diesel and the hydrogen as well. So this is like a validation. You can see the number of the carbon is constant. That means when we do the combination of the CO2 in the atmosphere, the CO2 from the carbon capture, and also the CO2 from the gas, when we do the combination of this one, and then we can get the constant of the carbon or carbon dioxide. Now I go to the last slide. Is the PISA can show the production based on the cost optimization. We can see the production from the biomass 0, and also from the biomass 1, from the OCGT with the CCS, and we can see the operation of the direct air capture. And if you remember, Tristan said actually they have any information when we run the PISA, we can do additional consider not only the CO2 or the production. So that's all for my presentation. Thank you very much.